Hi everybody, in this video we're going to do a basic example of how a derivative relates to physics. So in this question we have a rock is falling freely from rest near the surface of the earth. So somebody's holding a rock and they drop it. It's not a situation where they're throwing it, there's not an initial velocity. It's just a rock that's being dropped, and the question is, why does it have to be near the surface of the earth? Because of gravity. Gravity causes that rock to we're going to find out, it causes the rock to speed up as it gets closer and closer to the surface of the earth until it has impact. So we have a formula here. This is not exactly a traditional formula. This is just an example. So we have a rock that fell at this y equals 16 t squared feet during the first t seconds. So y is how far it's fallen, and t is the time at which we're telling how far it fell. So if you put in t equals 5 seconds into the fall, y is going to be how far it's fallen in those 5 seconds. If you put t equals 10, y will be how far it's fallen after 10 seconds have passed. So the question is, what is the rock's exact speed at t equals 1? Okay, exact speed is something that we have difficulty calculating. We've talked about this in some of the first videos. Exact speed is another way of saying instantaneous speed. You might recognize that. Instantaneous speed. All right, so why do you recognize it from? Section 2.1. We discussed the average rate of change. This should look very familiar to you, only we've been dealing with x's instead of t's. At the limiting value as h goes to 0, we found the speed at particular time t. So what we did in 2.1 was looked at the average speed over a time interval, and we let that time interval get smaller and smaller and smaller until we approached a distance between the times of 0. We let h go to 0, so our times got to the point where they were practically the same. That allowed us to find the speed at a particular instant of time rather than the speed over an interval of time. We define this as the derivative, which gives the function's instantaneous rate of change. So that's how we get instantaneous speed, by doing the derivative. So we're going to call this our function f of t is 16t squared. So we're calling it t, but it's just like we did with x. We're going to find the derivative of f of t. The change is going to be that instead of x plus h, we're going to have the t plus h. Remember, x is a more general formula, t is more specific because it's specifying that we're talking about a time. So our difference quotient is right here. Don't forget your limit as h goes to 0. So this would be the derivative of our function. The derivative of our function is an application, or one application of that, is to find the instantaneous speed at a particular time. So you have a choice here. You can plug in your time, so make t equals 1 everywhere, or you can work it out in general, leaving t, which is what I'm going to do, and then at the end we're going to plug in our time. Your choice, but I want to do it in general. That way, hopefully we can see a little bit more about what's happening to the speed over time. Okay, let's do this. So, let's see, limit as h goes to 0. So first of all, like usual, I'm going to work this out on the side, f of t plus h. So if f of t is 16t squared, what is f of t plus h? Wherever you see a t, replace it with t plus h. Don't forget to square the whole thing. So 16t squared plus 2th, whoops, that should be an h, plus h squared. What do we need to do with the 16? We need to distribute. All right. So we end up with 16t squared plus 32th plus 16h squared. I didn't mention, remember when you have parentheses squared, it means parentheses times itself, so I FOILed that. That's something we've talked about in previous videos. All right, so this is my f of t plus h, so I'm going to plug that into my formula for the derivative. So f of t plus h, 16t squared plus 32th plus 16h squared minus f of t. That's our original function. That was 16t squared all over h. In this problem, parentheses are not necessary anywhere. The first group, I put it just to help me remember that all of that is the first term alone, minus the f of t was just one term, so if I didn't put parentheses, it would still be correct. But if you have two terms in your f of t, that's when you have to put the parentheses, so be cautious. Limits as h goes to 0. All right, what can we simplify here? So the 16t squared minus the 16t squared, and that's it for now. If you want to go ahead and do the next step on that line, you probably could, but I like to rewrite it. You could factor an h out of the top, or you can reduce every single term by an h. So limit as h goes to 0 of, what survived? 32t plus 16h. I think we're done with algebra, so let's try and take the limit. What does that mean to take the limit? Let h go to 0, plug it in. If we let h go to 0, we end up with 32t plus 16 times 0, or 32t. What is this? This is the derivative of f of t. This is the instantaneous speed, or exact speed, at time t. So, let's think about this. At t equals 0, what's the speed? Plug in 0. You get 0. Speed is 0. That makes sense because your rock is starting from at rest. It's not moving initially, at the very beginning of its travels. Then you let the rock go. Gravity takes over and makes it start to fall to Earth. So at 1 second, plug in 1, you'd be at 32. At 2 seconds, you'd be at 64. 3 seconds, you'd be at 96. As t gets bigger, what's happening to your speed? Every time you make t bigger, your speed is bigger. So what is the rock doing over time? It's not just falling, it's falling faster and faster and faster until it hits the Earth. And that's it, it's done. Now this does not tell you when it hits the Earth. You would need more information for that. But it does tell you how fast it's going at any time t until it hits the Earth. What else can this tell you? One thing to point out, this formula does not take into account the directionality. So the rock is falling. This formula, this example, ignores the direction. It's just talking about speed. If it was asking you for velocity, this formula would involve a negative sign. Because the rock is falling, we consider that a negative velocity direction. So just something to keep in mind, and you'll see that later in other examples where we talk about velocity, whereas here we're talking about speed. All right, well, that's my example. I hope it helps you. Remember, study hard, and I'll see you in the next video.